This is the last unit of Unit 3, or the last part of Unit 3. We're on Topic H, talking about L'Hopital's rule. This is going to take us back to thinking about limits again, which we haven't done a lot of recently. We've been concentrating mostly on derivatives for the past couple of units. It turns out that actually once you know how to take a derivative, derivatives can actually be used as sort of a shortcut to find certain types of limits. So we're kind of coming full circle here. So, as an introduction, I want you to think about some of the limits that we did before, specifically the ones that yielded an indeterminate form. The one that we were most familiar with from Unit 1 was the 0 over 0 form. Right? We found that by doing enough algebra, we could often manipulate that until we could turn it into a finite number, and we could get actually a finite limit as an answer. That form, that 0 over 0, isn't the only indeterminate form. Basically, an indeterminate form is simply something that can actually take on virtually any value, depending on the context of the situation. And there's a whole bunch of them. The entire list is actually given to you here. These are all indeterminate forms. Things whose value isn't just a single value, but could be a lot of different values, depending on the context. The ones that we've seen a little bit before are 0 over 0 and the infinite over infinite forms. And those actually are the two that are the easiest to handle using something called L'Hopital's rule. So those two indeterminate forms, 0 over 0 and infinity over infinity, we're going to handle using this new rule, which is given to you right here. It says that if the limits of f of x and g of x, in other words, the top and the bottom, are either both 0, like this, or both infinite, like this, then we can actually find the limit of the fraction, f over g, by finding the limit of the derivatives, f prime over g prime. Sometimes it's going to turn out that this is easier to do, and it'll be a shortcut for us for finding the limit that we actually wanted. So, let's take a look. First of all, we have a limit that's one of our special limits. We've been using this one right along. I'll just remind you that we had seen numerically, and it's even on your page of notes for your tests, that the limit as x goes to 0 of sine x over x is 1. Let's take a look at this through the lens of L'Hopital's rule. Right now, if I were to plug in 0, this would look like sine of 0 divided by 0. Since sine of 0 is 0, this is a 0 over 0 form, an indeterminate form. Not only is it indeterminate, but it's one of the two cases where we're allowed to use L'Hopital's rule, right? We said either both 0, which is what we have, or both infinite, which we'll see an example of that in a little bit. So, this is indeterminate. It's a L'Hopital's rule form. So I'm going to say I could rewrite this limit, and I usually just put a little LH here to remind myself, and more importantly my reader, that this is what I'm doing, using L'Hopital's rule, as the limit as x goes to infinity of the derivative of the top over the derivative of the bottom. Well, the derivative of the top would be cosine x, and the derivative of the bottom is just 1. And now if I plug in 0, I get cosine of 0 divided by 1. Cosine of 0 is 1. So I get 1 over 1, or 1. Now, like I said, we actually already knew that was the answer to this one, but I just wanted to show you how that L'Hopital's rule worked on something where we actually were already familiar. Let's try a couple more. This next one, I claim we actually already know what the answer should be for this one as well. We know that when x goes to infinity and the powers are the same, we kind of had that old rule even back from pre-calc, that we should get the ratio of the leading coefficients. We should get 3 over 5. Let's see if we can look at this one also through the lens of L'Hopital's rule. Since x is going to infinity, the top becomes infinitely large, and so does the bottom. So this is the infinity over infinity case. Okay? It's the second case that L'Hopital's rule applies. So I'm going to say, great, let's go ahead and let's apply L'Hopital's rule. It says, still take the limit as x goes to infinity, but now I can do the derivative of the top and the derivative of the bottom. That would be 6x minus 6 for the top and 10x plus 1 for the bottom. By the way, as I'm talking about this, I do want to call one thing to your attention. This is not a quotient rule, right? We're not finding the derivative of this original function. We are literally finding the derivative of the top and the derivative of the bottom using L'Hopital's rule. It's not the derivative of the original function. All right, well, where am I at now? As x goes to infinity, top still goes to infinity. Bottom still goes to infinity. So I still have an indeterminate form. I still have infinite over infinite. So I can actually continue to apply L'Hopital's rule as long as it applies, and it does. Do another L'Hopital's rule. Limit as x goes to infinity. And if I take the derivatives again, the top just becomes 6, and the bottom is simply 10, which of course reduces to 3/5. And there's my limit. Again, we're expecting it, but this shows you how L'Hopital's rule can be applied to get that answer. All right, I want to look at one where it's not as obvious what I might have gotten in the past. This is one that we couldn't have probably just done by looking at it. I want to take the limit as x goes to 0 for this function. And first of all, I'm going to have you notice that if I tried to plug in 0, I would have e to the 0 minus 1 over 0 plus 0. E to the 0 is 1, so 1 minus 1 would be 0 on top. And of course, I also have 0 on the bottom. So this is one of those cases where L'Hopital's rule applies. Let's go ahead and do a L'Hopital's rule. If I take the derivative on the top, I'm just going to get e to the x. And the derivative on the bottom is going to give me 2x plus 3. If I now try plugging in my x equals 0, I'd have e to the 0 over 2 times 0 plus 3. E to the 0 is 1, and 0 plus 3 is 3. So my limit now is 1/3. So oftentimes it works out kind of nice and easily and relatively quickly. That said, I want you to recognize also that that doesn't mean that all of your old limit techniques are worthless and you'll never have to use them again. That's actually not the case. There are times where L'Hopital's rule can become a bit more of a problem. So don't throw out your old limit techniques. Just know that they are potentially made easier by L'Hopital's rule. All right, let's try a couple more. On number 4 here, I've got this big, relatively complicated fraction, and I'm taking the limit as x goes to 2. If I try to plug in the 2, I'd have 2 squared plus 2 minus 6 over the square root of 8 minus 2 squared minus 2. Top would be 4 plus 2. That's 6 minus 6 is 0. That's the square root of 4, which is 2. 2 minus 2 is also 0. So once again, we do have a L'Hopital's rule situation. You always want to make sure you check, because if it's not 0 over 0 or infinite over infinite, you can't use this method. All right, so I'm going to go ahead and say, yep, it applies. Let's do L'Hopital's rule. The top becomes 2x plus 1. And on the bottom, let's see, that square root is really a 1/2 power. So I'll have 1/2 times 8 minus x squared to the negative 1/2 times the negative 2x for the chain rule, and then minus 1. Let's see, if I try to plug in my 2 now, I would get 2 times 2 plus 1, so it's not 0 on the top. And on the bottom, I'm going to let those 2's cancel. I would have 8 minus 2 squared, or 4, to the negative 1/2 times negative 2 minus 1. Top is 5. On the bottom, that would be the square root of 4, so 2, but in the denominator, so 1 over 2 times negative 2 minus 1 is negative 1 minus 1, or negative 2. So I'm going to get negative 5/2 for that limit. All right, I've got one more example of these 0 over 0 and infinity minus infinity indeterminate forms right here. First of all, remember what the natural log graph looks like, right? If you don't remember, you can always graph one in your calculator. But the natural log graph looks like that. Right, it goes up slowly, but it does keep going up as x goes to infinity. So as x goes to infinity, this is like the natural log of infinity, which does go up to infinity. And same idea on the bottom. The natural log of infinity is infinity. Infinity plus 1 is still infinity. So I do have a L'Hopital's rule form, infinite over infinite. And I'm going to go ahead and do my derivatives. All right, for the top, I'm going to get 1 over 3x plus 5. And then the chain rule would give me a times 3. On the bottom, I'm going to get 1 over 7x plus 3. And the chain rule there will give me a times 7. The derivative of the 1, of course, is just going to be 0. All right, let's play around with that just a little bit. Really, this is 3 over 3x plus 5. And that's actually 7 over 7x plus 3. So I'm going to go ahead and say that to divide those fractions, I can multiply by the reciprocal. So I'm going to keep the 3 over 3x plus 5. And then I'm going to multiply by the reciprocal of that one. 7x plus 3 over 7. All right, let me multiply that out and see what we got. Top, if I distribute the 3, is going to give me 21x plus 9. And same thing on the bottom, I'm going to distribute the 7, 21x plus 35. All right, well, I still want x to go to infinity, so I still have infinity over infinity, but definitely a simpler function to work with, no more logs involved. Infinite over infinite, I'm allowed to use L'Hopital's rule. So that's just going to be 21 over 21, and that gives me 1 for my limit. Okay. So a few examples of using L'Hopital's rule in those 0 over 0 and infinite over infinite cases. What if I have one of the other indeterminate forms? The next two I want to look at are 0 times infinity and also infinity minus infinity. Now keep in mind, L'Hopital's rule does not apply directly to those. It only applies to 0 over 0 and infinite over infinite. So what that tells me is I'm going to have to convert these forms to something that looks like one of those, and then I can apply that L'Hopital's rule. Typically, this involves converting one of the factors to division by the reciprocal, very common. So let's look at a couple of these. In this first one, I've got the limit as x goes to 1 from the left of 1 minus x times the tangent of pi x over 2. 1 minus x, of course, would be 0. And the tangent of pi x over 2, if you think of approaching 1, that would be the tangent of pi over 2. And tangent has a vertical asymptote at pi over 2, right? Again, just a reminder of what that looks like. You can generate this on your calculator or Desmos or whatever. But that's one period of the tangent function. Keeps repeating over and over, right? So as we approach 1 from the left, at pi over 2, tangent of pi over 2 is going off to infinity. So that's actually the 0 times infinity case. It's not a L'Hopital's rule case, but it is indeterminate. I'm going to say to myself, is there any way I could change this just a little bit to turn it into something so I could use L'Hopital's rule? Well, with trig functions, we know they all have reciprocals. The reciprocal of tangent is cotangent, right? That's just the reciprocal. So if I wanted to, I could rewrite this. And I could put the 1 minus x, leave that on top where it is. And instead of multiplying by tangent, instead I could divide by cotangent. Again, those are reciprocals, so that's the same thing. Well, what have I got now? 1 minus x is still 0 on top. But the cotangent graph has its asymptotes at plus and minus pi, not pi over 2. So when I plug in the 1 and I want cotangent of pi over 2, again, you can generate this graph with your calculator, Desmos, whatever, right? It looks like this. I'm so sorry, it does not look like that. It looks like this. The asymptote is at pi, not pi over 2. And the cotangent of pi over 2 is just 0. So I have the 0 over 0 case here. Apologize for my bad graph. And again, you can generate that graph, calculator, Desmos, whatever. All right, well, now that I've got 0 over 0, I am allowed to use L'Hopital's rule. So let's do that. I have the limit as x approaches 1 from the left. And the derivative on the top is just negative 1. The derivative on the bottom would be negative cosecant squared of pi x over 2. And then I'm going to do a chain rule here, multiply that by the derivative of what's inside, which would be pi over 2. I can let my negatives cancel out just a little bit. And that would give me, let's see, the reciprocal of cosecant is sine. So if I want to bring it to the top, that would be the limit as x approaches 1 from the left of sine squared pi x over 2. And dividing by that, the reciprocal of pi over 2 is 2 over pi. That's a lot nicer. Sine is never undefined, right? So what have I got here? If I plug in the 1, I'd have sine squared of pi over 2. Since x is 1, times 2 over pi. The sine of pi over 2 is 1, so that's 1 squared times 2 over pi. And as my limit, I get 2 over pi. So a bit more work in this case. I have to get the fractional form, in this case 0 over 0, although infinity over infinity would have been fine as well. Do my L'Hopital's rule then on that fractional form, and I was finally able to get to that answer. All right, what about the second one? X is going to infinity, so I've got x going to infinity minus the square root of infinity is also infinity. So here again, I have an indeterminate form. Infinity over infinity is one of them, or excuse me, infinity minus infinity. It's one of those indeterminate forms, but it's not a L'Hopital's rule form. I need a L'Hopital's rule form. So let's see what we can do. I'm going to go ahead and just put this over 1 to get me started. I know I need a fraction for L'Hopital's rule anyway. And I'm going to say that in this case, I think maybe multiplying by the conjugate is a really common trick that we use when we have this sort of a situation with the radicals. So I'm going to go ahead and multiply by the conjugate, x plus the square root of x squared minus 3x, top and bottom. All right, let's see. First, this is going to give me an x squared here. As is always the case with conjugates, right? The outers and the inners are going to be opposites, so they add up to 0. And then the lasts, I'm going to have a minus the quantity x squared minus 3x. The x squareds, of course, will subtract away, so the top just becomes a positive 3x. All right, well, at least I've got a fraction. And if you think about this one, you do have an infinity over infinity case, right? The top definitely goes to infinity, and the bottom is infinity as well. So, by doing that algebra, what we've done is we've changed our original indeterminate form into a new indeterminate form, but one that has the advantage of being able to be done with L'Hopital's rule. Okay. I'm going to go ahead and try L'Hopital's rule here for you, and let's take a look. The derivative of the top is just 3. On the bottom, I would have 1 plus, and this is a little bit ugly, I have 1/2 times x squared minus 3x to the negative 1/2. And then a chain rule, 2x minus 3. All right, well, let's see here. That's actually 3 over 1 plus 2x minus 3 over 2 times the square root of x squared minus 3x. All right, I want to talk to you a little bit about what's going to happen here. If I were to just continue to do this, I would now say, all right, what about this piece here? Right, the 3 and the 1 are fine. But that thing is going to continue to cause me problems. No matter what I do, every time I take a derivative of that square root, I'm going to get a 1/2 times whatever the square root was to the negative 1/2. I'm going to get a new square root, right? And this little piece right here is still infinity over infinity. It's still indeterminate. And I'm going to continue to get indeterminate form after indeterminate form after indeterminate form if I continue to try to use L'Hopital's rule on that. So what I'm going to do instead is I'm going to say, you know what? Sometimes the old ways really were best. Maybe instead of using L'Hopital's rule here, which is going to get me into sort of this infinite cycle, maybe I'd be better off going back and using our old methods of finding limits. So I'm going to say, tried it, don't love it. Okay. Instead, do you remember the technique that we used when we had infinity over infinity way back in Unit 1? We divided by the highest power of x in the denominator. So we would have divided by x over x. Let's try that instead. On the top, 3x divided by x is 3. On the bottom, x divided by x is 1, plus the square root of. And then remember, under the radical, you actually have to divide by x squared. We're dividing by the square root of x squared. So that'll become a 1 minus 3 over x. Now as x goes to infinity, that fraction goes to 0, and I just end up with 3 over 1 plus the square root of 1, or 1, giving me 3/2. Okay. So I kind of mentioned this in the first half today. Sometimes, even with L'Hopital's rule out there as a tool, it still is a good idea to remember your old techniques. L'Hopital's rule is great, but there are times where it doesn't work out so well. And it's really common with these square roots because derivatives of square roots continue to have square roots in them forever. All right, we have one more set of indeterminate forms that we want to look at. And these are the exponential ones. 0 to the 0 power is an indeterminate form. So is infinity to the 0 power, and also 1 to the infinite power. None of those can simply be evaluated. They're all indeterminate. Again, none of these are L'Hopital's rules forms yet. So we're going to have to do a little work to get them there. Okay, I've got a rewrite thing here. I actually don't love doing this anymore. I need to rewrite my notes. I'm going to go ahead and suggest a slightly different method that I'm finding students tend to like a little bit better. As I look at this first problem, as I let x approach 0 from the right, certainly this is a 0 to the 0, one of my indeterminate forms. Anytime you have any of these exponential indeterminate forms, your best bet is always going to be to follow this procedure. Name your limit. I'm going to call it L. And the reason I did that is because I wanted an equation, because I would like to take the log on both sides, natural log, in fact, on both sides. So I'm going to take the natural log of L, my limit, and then I'm also going to take the natural log of x to the 2x. By the way, I know that was just a little bit of sleight of hand. I did bring that natural log inside the limit. If you'll accept it, I'm just going to tell you that that is a legitimate, algebraically correct thing to do. All right, here's where this is helpful. I can now use a log property, right? I know that power property of logs. I can take that 2x, I can bring it down in front as a multiplier on that natural log. So what I've accomplished so far is I no longer have an exponential at all, so there's no way I could possibly have an exponential indeterminate form. However, fair warning, this is one of those out of the frying pan into the fire problems, because look what I do have. As x goes to 0, I have 2 times 0, or 0. And as x goes to 0, again, remember your natural log graph, right? What does your natural log graph look like? As x goes to 0 from the right, that natural log graph goes down to negative infinity. So now I have a different indeterminate form. I have the multiplicative one. What we just finished saying on the previous page is when I have that kind of an indeterminate form, usually the best thing to do is to use the reciprocal of one of the elements, one of the factors, to create a fraction. That's what I'm going to do here. The natural log of x, I don't really want to do too much messing with that. So I'm going to leave 2 ln x on top. But if I move that x into the denominator, I could just call it an x to the negative first, right? Those are algebraically equivalent. To move the negative exponent back to the top, I would just make it a positive first power. So those really are the same. Well, now what have I got? We've already said natural log of x goes to negative infinity near 0. And this is like 1 over x. 1 over 0 also goes to infinity. Either you know, or again, you can think about the graph. The 1 over x graph looks like this. And as you approach 0 from the right, it goes to infinity. So this is now the indeterminate form, negative infinity over infinity. So we have actually managed to go through 3 separate indeterminate forms in this problem. Right? But I'm happy with the last one because this last indeterminate form that I've gotten to finally is one where I can use L'Hopital's rule. So we're going to do that. If I'm using L'Hopital's rule, I can now say the derivative on the top would be 2 times 1 over x. And the derivative on the bottom would be negative x to the negative 2. All right, I'm going to do a little bit of algebra here. The top is really 2 over x. And I could take that x to the negative 2 and bring it to the top as an x to the positive 2. So I have a negative x squared. It's just like multiplying by the reciprocal, right? Bringing the negative exponent to the top. Well, now I could reduce. I can cancel out one of those x's. And I have negative 2x over 1. And so as x goes to 0, that just becomes 0. Now I'm not quite done yet. I wanted that limit that I called L. And right now I have the natural log of L. So I'm just going to exponentiate both sides on a base of e. The e and the ln are inverses, so that allows me to solve for L. L is e to the 0 power, or 1. All right, so a bit more work with those exponential indeterminate forms. Anytime you see one of them, and we will do one more, but anytime you see one of those, you always want to start by giving it a name, call it L or whatever you want, and taking the natural log of both sides. That's going to be essential to being able to eventually get a L'Hopital's rule form that you can work with. So let's try that one more time. X is going to infinity here. So let's see, inside my parentheses, I have 1 plus 1 over infinity, 1 plus 0, to the infinity power. And so I have 1 to the infinity, which is an indeterminate form. Because it's an exponential indeterminate form, I'm going to give it a name. I'm going to call it L. Just sneak that in here. And let's take that natural log on both sides. All right, I am going to use the same trick. I'm going to go ahead and say, let's take first of all that X, and I'm going to bring that down as a multiplier, just using a log property. I now have X is going to infinity times the natural log of 1 plus 0, or natural log of 1, but natural log of 1 is 0. So I now have a new indeterminate form, infinity times 0. We know we have to create a fraction, so let's do that next. Don't like much to mess with the natural logs. I'm going to leave that natural log right where it is on the top. And on the bottom, I'll move that down and make it an x to the negative 1 again. Again, very common trick. All right, natural log of 1, that's 0. That's like 1 over infinity, that's 0. Still an indeterminate form, but finally one that allows me to use L'Hopital's rule. All right, so let's see here. If I apply L'Hopital's rule, I need the derivative of the top. So that's 1 over 1 plus 1 over x times the derivative of the inner function. The derivative of the 1 is 0. And if you kind of mentally think about this 1 over x as being an x to the negative first, its derivative would be negative x to the negative second. The derivative of the denominator is negative x to the negative second. Well, that's kind of nice because I can reduce, divide those out. And that means that the natural log of L, let's see, as x goes to infinity, that's just 1 over 1 plus 1 over infinity is 0. Or in other words, the natural log of L is 1. Again, I actually wanted L, the original limit, so I'm just going to go ahead and exponentiate both sides on a base of e. The e and the ln are inverse functions, so that solves for L. L is e to the first, or just e. So my limit here is e. All right, so those are all of our indeterminate forms. They can't all be solved directly with L'Hopital's rule, but with the appropriate algebra background and some manipulating, you can get them to be either 0 over 0 or infinity over infinity, and that allows you to use L'Hopital's rule. That brings us to the end of Section H and also to the end of Unit 3.